Welcome to the deep dive. We're going to be diving into Boltzmann machines today.
Oh, cool.
Yeah, Boltzmann machines.
I've heard of those.
It's a pretty fascinating concept, and I think it's something that's, key to understanding how AI learns.
Yeah.
And you want a clear and simple explanation, and we're going to try to give you that today. So buckle up, get ready to unlock some of the secrets of how these powerful networks learn.
Sounds good.
Almost like a system in nature finding its perfect balance.
Yeah, I guess like an ecosystem or something.
Exactly. So to kick things off, imagine like a network of neurons.
Okay.
Like tiny little light switches that can be either on or off.
Okay, got it.
But instead of just like a simple on or off switch, these operate probabilistically.
Probabilistically.
Meaning there's a chance that they'll be on and there's a chance they'll be off. And that all depends on the connections between them and the overall energy of the network.
Okay, so it's not just a binary on or off.
Right.
There's some probability involved.
Exactly. And why is that important?
Well, I mean, the real world is full of uncertainty.
Right.
You think about recognizing an image. It's rarely just a clear cut, oh, this is a cat.
Right.
It could be like a cat that's kind of blurry, or maybe it's like half hidden behind something. So Boltzmann machines, they embrace that kind of probabilistic nature.
Okay.
And that allows them to model these complex data distributions,
Yeah.
which basically means that they can, capture that inherent fuzziness of real world phenomena.
So it's not just about finding the one right answer.
Right.
It's more about understanding the likelihood of different possibilities.
Exactly. And that's where this idea of energy comes in.
Energy.
Yeah. And, in physics, systems tend to move towards states of lower energy. You think about a ball rolling down a hill. It's going to want to end up at the bottom in the valley. It's not going to want to stay at the top of the hill. And it's kind of the same thing with a Boltzmann machine. It's always searching for these configurations that minimize that energy function.
So the network is always trying to find the most stable, low energy state.
Exactly. And those low energy states, they correspond to the most probable configurations.
Okay.
The ones that, best represent the patterns in the data. That's kind of how the network learns.
Okay.
It's like finding that perfect balance.
Now, you mentioned this is really important for AI.
Yeah.
What makes Boltzmann machines so important in this field?
Well, they introduce a completely different way of thinking about how machines learn.
Okay.
They bring in these ideas from statistical mechanics, stuff like the Boltzmann distribution, to build networks that learn by finding those, most probable configurations. It's
I see.
Imagine teaching an AI to, classify images of cats and dogs.
Okay, yeah.
A traditional neural network that might try to draw a hard line between the two. But a Boltzmann machine, because it's working probabilistically, it can learn to capture the subtle differences within each category.
Okay.
Recognizing that not all cats or dogs look exactly the same.
Yeah, that makes sense. It's not just memorizing the examples.
Right.
It's understanding the probability.
Exactly. It's about understanding that underlying probability distribution of the data.
Okay.
And that makes Boltzmann machines much more robust. They're better equipped to handle that complexity of real-world data, where things are rarely black and white.
Right.
It's all shades of gray out there. And that's what made them, so groundbreaking. They really paved the way for this whole new approach to AI, one that embraces uncertainty and learns from these probability distributions. It's a big shift.
But, I've read before that Boltzmann machines can be really complex.
Yeah.
And computationally demanding.
They can be, yeah.
How did people overcome that?
You're right. That original Boltzmann machine, with all its interconnected neurons, that could be a real computational beast.
Right.
So that's where restricted Boltzmann machines came in.
Restricted Boltzmann machines.
Yeah, or RBMs.
RBMs.
Okay.
So are those a simplified version?
Yeah, you can think of them as a streamlined architecture.
Okay.
So instead of every neuron being connected to every other neuron,
yeah,
we impose some restrictions.
Okay.
And that makes them a lot more manageable computationally.
Right.
But they still keep those core principles of, energy-based learning and probabilistic inference.
So we're sacrificing some complexity.
To some extent, yeah.
For practicality.
Right. But it's not just a computational fix.
Okay.
RBMs are incredibly powerful on their own.
Okay.
Imagine trying to, identify those fraudulent transactions. An RBM can learn to pinpoint those subtle patterns in the data
Okay.
that differentiate like a fraudulent transaction from a legitimate one.
Oh, they're like little expert detectives
Yeah, sifting through all that data to find those signs.
looking for those clues.
Exactly. And that ability to extract like meaningful features
Yeah.
from complex data, that makes RBMs really valuable for a whole bunch of AI applications.
Okay.
Like, think about building a recommendation system
Mhm.
for like a music streaming service.
Right.
An RBM can analyze, your listening history,
Yeah.
pick up on those hidden preferences that you might not even know you have.
That's got to be how Spotify knows what I want to listen to before I do.
Exactly. It's finding those connections
Yeah.
that you wouldn't have even noticed.
Wow.
And that's just one example, right?
Sure.
RBMs are also used in image recognition,
Okay.
natural language processing, drug discovery, all sorts of stuff.
So it sounds like they're more than just a stepping stone.
Yeah,
They're like driving real-world applications.
absolutely. They've gone from theory to these practical tools that are, shaping the future of AI.
So we've gone from these probabilistic networks inspired by physics to their more practical counterparts, RBMs.
Right.
But what makes RBM so versatile?
Yeah.
Is it just the computational efficiency?
Well, I think it's more than that.
Okay.
RBMs really capture the essence of how systems learn in the real world.
Okay.
Like, think about how we learn as humans.
Yeah.
We don't just memorize facts, right?
Right.
We build this probabilistic understanding of the world.
Okay.
We're making predictions based on, incomplete information.
Right.
And we're constantly updating what we believe
Yeah.
as we, see new evidence.
Okay.
And RBMs, they operate in a really similar way.
All right.
They learn to represent data in terms of probabilities,
Okay.
which lets them deal with uncertainty, extract those meaningful features,
Right.
and even generate new data that follows those patterns.
So it's like they're capturing that essence of human learning
Exactly.
and applying it to machines.
And that's why they're so impactful, right?
Right.
They're not just crunching numbers.
Okay.
They're building this probabilistic model of the world.
Okay, that's really interesting.
Yeah, it's kind of like how we do it.
I'm starting to get it. But I do have a question.
Yeah,
We've talked about how they learn from data,
right.
but how are they actually used?
Oh, yeah, good question.
Can you give me an example?
Sure. Let's take medical diagnosis.
Okay.
Imagine you've got this huge data set of medical images,
Okay.
like x-rays, right?
Yeah.
And you want to train an AI to detect signs of lung cancer.
Okay.
An RBM can be used to analyze those images,
Right.
learn to identify the patterns that might, indicate a tumor.
Okay.
It's not just memorizing images.
Okay.
It's building that probabilistic model
Right.
of what a cancerous growth looks like.
Okay.
And that allows it to detect variations and anomalies.
That a human might miss.
Exactly.
So it's like having an AI radiologist
Yeah, working alongside doctors.
to make diagnoses more accurate.
Exactly. And
Yeah.
that's just one example. RBMs are being used to personalize online recommendations, improve financial forecasting models,
Okay.
even create realistic images for, computer graphics.
Wow.
They're everywhere.
It's incredible to think that these concepts from physics
Yeah,
are now driving these real-world applications.
it is. It really speaks to the power of, thinking across disciplines
Right.
and finding inspiration in unexpected places.
But I'm curious, with all these applications, what's next for RBMs?
That's a great question.
What are the limitations that people are still trying to overcome?
Well, one of the big challenges is scaling these models
Okay.
to handle even larger and more complex data sets,
Right, because we keep generating more and more data.
Exactly. We need algorithms that can keep up.
Mhm.
So researchers are exploring new ways to train RBMs more efficiently
Okay.
so they can tackle, bigger and bigger problems.
So it's like a race
Yeah.
to
you
keep
got it.
up with all this data.
Exactly. And another area of research is exploring new types of Boltzmann machines
Okay.
with different architectures and learning rules.
So they're trying to make them even more powerful.
Exactly. And that's what makes it so exciting, right?
Yeah.
There's always something new to discover, new possibilities, new applications.
It sounds like the field is constantly evolving.
It really is.
So for someone like me who's just starting to learn about Boltzmann machines, what's the key takeaway? What's the one thing to remember?
I'd say the key takeaway is this. Boltzmann machines represent a real shift in how we think about AI.
Okay.
Instead of looking at learning as just memorizing rules or drawing lines,
Right.
they embrace that uncertainty, that complexity of the real world.
Hmm.
They learn by finding the most probable configurations.
Okay.
And that allows them to handle, that ambiguous data,
Okay.
extract those features, and even generate new data based on what they've seen.
Wow.
It's pretty amazing.
It's like they're teaching machines to think more like humans,
Yeah, I guess you could say that.
recognizing that the world isn't always black and white.
Exactly. And as we keep exploring the potential of these Boltzmann machines,
Yeah.
I think we're going to see some even bigger impacts on how we build, these intelligent systems.
It's really fascinating stuff.
It is.
So where does this leave us? What's the next chapter?
That's the exciting part, right?
Yeah.
We're still writing it.
Okay.
New research, new applications are coming out all the time.
It's a wide open field.
Exactly.
Sounds like we've only just scratched the surface.
I think that's a good way to put it. Think about all the data out there.
Yeah.
Boltzmann machines give us this powerful way to understand and use it,
Okay.
to find hidden patterns
Mm-hmm.
and drive innovation in ways we can't even imagine yet.
It's incredible.
It really is.
Well, that brings us to the end of our deep dive into Boltzmann machines.
Yeah, it's been fun.
We hope you enjoyed it and learned something new.
Yeah, keep exploring, keep learning, keep asking questions.
You never know. You might make the next big breakthrough.
That's right.
Until next time, keep diving deep.